Good morning, everyone. Today, we will present on correlation and time series data analytics on our project, Waste Watcher. About the dataset contains 430 records. Waste level information including waste level, bin location, timestamp, and capacity in each hour, along with their corresponding weather conditions, including temperature, precipitation, and humidity. For the compact data characteristic, the compact data characteristic in our dataset is the diverse source. The data is integrated from the waste level information using ultrasonic sensor as primary source and weather condition data from weatherapi.com as secondary source. Compact data exploration. First step in data exploration, we find that the dataset does not contain any missing value. Then we apply the correlation metric to analyze the correlations and is reveal the interesting relationship among the waste level and weather conditions. The temperature show a moderate positive correlation with waste level. On the other hand, the humidity level has a moderate negative correlation with waste level, while precipitation has a very weak correlation with the waste level. Next, we identify the trend of the data in our dataset. The trend of the humidity level tends to be lower during daytime hours and increase during nighttime periods. On the right side is the trend of precipitation, which consistently remain low or at zero. However, on the 19th and 20th of April 2024, there is a notable increase in precipitation compared to other days, attributable to rainfall events. The trend of temperature consistently remains high, typically ranking between 30 to 40 degrees Celsius. Furthermore, temperature tends to be higher during daytime hours and lower during nighttime periods. The interesting thing is that the trend of waste level remains relatively consistent each day, which peak during mealtime and none at night. For the compact data preprocessing, the first step in our preprocessing step is to set the role of bin ID, lat, long, and capacity as metadata, to leave them out when modeling, and set the role of waste level as label attribute. The second step is that we remove the duplicate record with the same timestamp from the dataset to ensure the data integrity. For the next step, as our dataset is a time series data, we apply two time series preprocessing technique to the dataset, but separately. The first one is applied with windowing with timestamp as the index attribute, the window size of 12, and the waste level as horizon attribute. The other one is applied with classic decomposition with the timestamp as the index attribute, the decomposition mode as additive, and the seasonality of 24, which represent the hourly data. Next is the analytic technique. Correlation metric is a technique for addressing the relationship between variables in a dataset by calculating the correlation coefficient to measure the strength and direction of linear association between variables. To interpret the correlation coefficient, it is a spectrum of value from -1 to +1. The more range from 0 indicate the more strength of the correlation. The negative value indicate the opposite relationship, and the positive correlation indicate the linear relationship. The correlation metric is normally visualized using heat map, as you can see here. Next is the time series windowing. The time series windowing is a technique to divide the time series data into smaller segments called data window. The data window consists of input feature representing past time step and output target representing future time steps. It can be used to enhance the accuracy of prediction model by capturing temporal dependencies. For the step of the technique, first we need to choose the window size or the number of time points to be included into each window. The second step is to choose the stride or step size, which determines how much the window moves at each step. The last step is to slide the window across the data to create the window. For the time series decomposition is a technique to disassemble a time series dataset into its fundamental component. This component will help us gain better insight into the underlying pattern and structure of the data. The component consists of trend, which is the long-term pattern or directionality in the data. Seasonality, which is the repetitive and periodic fluctuation at regular intervals. Residual is the random fluctuation or irregularity that cannot be attributed to the trend or seasonality. For the step of time series decomposition, first we need to identify the component vector. The composition should be additive or multiplicative. Then we can estimate the trend component by method like moving average or loss. The third step is to estimate the seasonal component by averaging the deviation from the trend over corresponding period. The last step is to calculate the residual component by subtracting the trend and seasonal component from the original data. Next is the demonstration of our project.
This is the demo on how we perform correlation analysis and time series analysis in RapidMiner. So first, let's go for the correlation analysis. The data is retrieved, then we remove the duplicate items based on the timestamp, and then the data goes into the correlation metric. But we just select the 4 attributes to visualize, which is humidity, waste level, precipitation, and temperature. Then, on the time series analysis, the data is also retrieved. Then we set the role of the unimportant attributes to metadata, including the bin ID, the ID, latitude, longitude. Then we remove the duplicate items based on the timestamp. After that, we copy the data into 3 sets. The first one will go to evaluate without applying any pre-processing technique. So we'll evaluate all of the data set with the cross validation of 10-fold and the random forest with the number of trees equal to 20, the least square criterion, and the maximal depth of 10. The second dataset will go into the windowing operator. So with this, we set the index attribute to the timestamp, and we set the unit to example base, the window size to 12, and the step size to 1. We also set the horizon attribute to level. For the third one, classic decomposition, we set the index attribute to timestamp, the decomposition mode to additive, and the seasonality to 24, as the data is hourly data. So let's run. So first, let's go to the correlation metric. Here, as you can see, it will show the heat map with the correlations of the 4 attributes we selected earlier. Then the cross validation of this is the performance of the model without any time series pre-processing technique applied. The root mean square is about 1.97. The absolute error is 1.228, and the relative error of 55.72%. What about the windowing? The windowing has a lower root mean square error, which is the 1.652, the absolute error of 1.067, and the relative error of 47.63. So you can see that the error is reduced which means that the model is better. After that, let's go to the last technique, which is the classic decomposition. So in this, the root mean square error is only 0.935. The absolute error is about 0.439, and the relative error of 23.88%. So you can see that it reduced to almost half of the first and second model. For the evaluation of our project, as you have seen from the demo, the evaluation of our project is done using cross validation with 10 folds and the random forest of 23 least square criterion and 10 maximal depth. So we are evaluating by predicting the waste level and measure the regression performance. Here is the evaluation result when there is no time series pre-processing technique applied to the dataset. The root mean square error is at 1.972 with the deviation of 0.432, and the absolute error is 1.228 with the deviation of 0.233, and the relative error of 55.72% with a deviation of 8.7%. So you can see that it is actually okay, but not good enough. So what about we apply the time series pre-processing techniques that we learned, which is windowing and decomposition, to our dataset before modeling? So when we apply windowing to the dataset, the root mean square error is reduced to 1.652 with the deviation of 0.241, and the absolute error is reduced to 1.067 with the deviation of 0.198, and the relative error is reduced to 47.36 with the deviation of 9.32%. So you can see that the relative error is reduced for almost 10%, which is better. And what about if we apply classic decomposition to our dataset? So the root mean square error is reduced to 0.935 with a deviation of 0.546, and the absolute error of 0.439 with the deviation of 0.14, and the relative error of 23.88% with a deviation of 7.78%. So you can see that it is the best from or of the test evaluation that we have done. What about the possible applications from our project? The environmental policy development. So first, insight application. The analysis provides valuable insight into how weather affects waste production. Second, policy impact. It helps policymakers to create effective environmental regulations. And the last one, policy development. So it enables targeted policies to improve waste management, encourage recycling, and address weather-related waste issues. The next application is urban planning. So weather consideration highlight the importance of including weather factors in urban development plan. The infrastructure resilience. So assist urban planners in building resilient waste management infrastructure. And the last one is to have the sustainable system. So it supports the creation of sustainable waste management system, enhancing urban environment quality. The last application from our project is to promoting sustainable practices. First, community impact. It encourages sustainable waste management practice in communities. The behavior change. It empowers individual and organizations to adopt eco-friendly behavior. And the last one is sustainable initiative. It promotes initiatives like composting, waste reduction campaigns, and weather responsive waste disposal methods to create a greener society. And this is our references. Thank you for watching.